All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for HL Chemistry. Hope you guys are doing well. It's been a while since I've made any videos, but wanted to put this one together for you guys, and I'm doing this a little bit differently for this particular topic because I was looking through the material, and since the majority of you guys have taken AP Chemistry, you guys did well in AP Chemistry, the content that's covered in sections 3.1 and 3.2, I would say like 3/4 of it are things that should be prior knowledge. You've seen it in Honors Chem before, you've seen it in AP Chemistry before, and so as I was scanning through it, I really wanted to focus in on the things that maybe we were less familiar with. And so in section 3.2, it does begin to introduce this idea of the property of the oxides when you start to look at it across a period and how they change from being basic, amphoteric to acidic as you're looking across a period. And so I wanted to look at the reactivities of these oxides and how we could determine whether or not an oxide is basic, amphoteric, or acidic simply based on its location on the periodic table. I think that was going to be the first place where that was going to be something that was unfamiliar to us. So I'm excited to show you guys this stuff. I think it's pretty interesting of how it all relates back to periodic trends and our understanding of how the electrons move and Coulombic attraction and things like that. So it really just builds on the information we've been talking about already. So let's dive right in here. So the first thing that we're going to note is that when an element bonds with oxygen, oxides are formed, right? That makes sense. Whether it's a metal that's bonding with oxygen or a non-metal bonding with oxygen, you get some sort of compound that's called an oxide, right? So there's no surprise there. Now, for our ionic compounds, so that would be with your substances of sodium, magnesium, and aluminum, it forms an ionic compound because you've got a metal and a non-metal, or even more specifically, a cation and an anion. They tend to have giant ionic structures, right? So they have these large ionic structures. They're held together really tightly because you've got transfers of electrons from the metal to the non-metal. And then you've got these Coulombic attractive forces that are much stronger because you've got these charge differences that you're dealing with because oxygen has a 2- charge. And so as a result, the ionic compounds of sodium oxide, magnesium oxide, and aluminum oxide have high melting points because of those giant ionic structures. Your covalent compounds, which are going to be the oxides that are formed from the non-metals, right? So those would be your oxides of phosphorus, sulfur, and chlorine. Because they're nonmetals, because they're covalently bonded, they form a molecular covalent solid. And what that typically means is they're going to have a significantly lower melting point than our giant ionic structures, right? And then our other oxide that gets formed is from silicon. You get silicon dioxide, which would be quartz. So it's a metalloid. It's going to have a covalent structure. I believe the term that you might remember might be a covalent network solid. And it's going to have a very high boiling point. Another example of something with a covalent network solid structure would be something like diamond, for example, right? So you've got the ionic and the metalloid having high melting points, but then your covalent compounds forming your molecular covalent solids, which have lower melting points. All right, so when we start talking about bonding and identifying whether or not the compound is going to be acidic or basic, we have to think about it in terms of its ionic or covalent character in terms of the bonding. And so the ionic character of a compound depends upon the difference in electronegativity between the elements that are bonded. And if you recall, electronegativity is simply the ability of an atom to draw electrons to itself within a chemical bond. So you start thinking about bonds, the more electronegative element is going to try to hoard the electrons to itself. It's going to try to have greater ownership of those electrons within the bond. And so we know that oxygen has an electronegativity value of 3.5. And so if we start to compare the ionic character of the oxides, it's going to decrease from left to right. And if you think about this, our elements that are to the left have lower electronegativity values, and that should make sense to us because our metals don't typically want to draw electrons to themselves. Typically, they're trying to get rid of electrons in bonding, right? So it's going to decrease from left to right as the electronegativity values of period 3 approach the value of 3.5, right? So kind of keeping that in mind, that would mean that the most ionic character bond between oxygen would take place between, at least on period 3, would be between sodium and oxygen, because that'd be the greatest difference in electronegativity between those two elements. Now, if you were to move down a group, for example, so if you start looking at like sodium, potassium, rubidium, the oxides would become more ionic as you would move down a group, because again, the electronegativity is decreasing as you move down a group. So then rubidium would have the most ionic character of its oxide, right? Because the difference in electronegativity would be greater. And another thing that chemists can use to measure ionic character, certainly we can use this electronegativity difference, but another test that could be measured is the electrical conductivity of an ionic solid, right? Well, specifically a molten ionic substance, right? So you convert the ionic substance to a liquid and you measure its electrical conductivity. And so what we're saying here is if we were comparing the group 3 elements, or the period 3 elements, excuse me, we would say that sodium would have the greatest ionic character because of the fact that it's because of the difference in those electronegativities, its electrical conductivity should be greatest, right? If you're moving within the same group, the rubidium oxide would probably have the greater ionic character because of the differences in electronegativity there. So electrical conductivity is just another way to measure the ionic character of a bond. Now, we've looked at this, we've talked about these oxides, and so it's important to recognize that when the metallic elements which form those ionic oxides, when they are placed in water, it reveals kind of their basic character, right? So they're basic in nature. For your non-metallic elements, so your oxides that are from phosphorus, sulfur, and chlorine, when they're placed in water, because of their covalent bonds, what we see is that those oxides tend to be acidic in nature. So, and to break this down by period 3, sodium and magnesium, those oxides are basic. Aluminum silicon oxides are what are known as amphoteric. And what that simply means is that they can be both basic or acidic depending on other factors that are playing out in the reaction of those oxides. And then phosphorus, sulfur, and chlorine, those oxides are acidic, following with the trend that we were just talking about. All right, so something that you should be able to do now that we've kind of understood what's going on within this period, we want to be able to construct equations to help explain the pH changes for reactions of sodium oxide, magnesium oxide, tetraphosphorus decaoxide, and the oxides of nitrogen and sulfur with water, right? So these are reactions that you would need to kind of have memorized and understanding what's happening when these elements react, or these compounds react with water. What kind of compound do they form, and is it acidic, basic, or is it amphoteric? All right, so for our basic oxides, right, our basic oxides are going to dissolve in water, and when they do, they're going to form a basic or an alkaline solution due to the presence of hydroxide ions, right? And so if we start thinking about this from the perspective of pH, that means that once these substances dissolve in water and they react, you're going to get a pH that's above 7, right? And so, for example, when you place sodium oxide in water, you get the production of 2 moles of sodium hydroxide, right? So that's a relatively strong base. We know it's a strong base because it completely dissociates in solution. Magnesium oxide, when it's placed in water, you get the formation of magnesium hydroxide. Again, relatively strong base. And so when it's placed in water, you get the production of those hydroxide ions, giving you a solution that has a pH that's above 7. And so the basic oxides, I think, are pretty straightforward. Their reactions are not very complicated, right? So it's the oxide plus water makes the hydroxide base. Pretty straightforward, kind of a pattern that we can follow to determine those oxides. We could do the same thing for any of the other periods as well, right? With the metals, you could do lithium oxide plus water would make lithium hydroxide. Now, your acidic oxides are a little bit more complicated, a little bit more specific, so you have to kind of pay attention here. So the non-metallic oxides react readily with water to produce acidic solutions, which have pHs below 7, right? So that means the water, in a sense, is going to be donating protons over to the nonmetallic oxides, and then it produces solutions that have pHs below 7, right? So for example, the tetraphosphorus decoxide plus 6 water yields phosphoric acid, 4 moles of phosphoric acid to be precise, right? Now, phosphoric acid would be, so it's one of our acids. Then you've got, if you got P4O6, so tetraphosphorus hexoxide plus 6 waters, you end up with 4 moles of phosphorus acid, right? So kind of here, those are 2 different oxides of phosphorus. Here are the ones for sulfur. You've got sulfur trioxide plus water makes sulfuric acid. Sulfur dioxide plus water makes sulfurous acid. And then, so nitrogen dioxide plus water makes nitrous acid and nitric acid at the same time. So again, all of those solutions that are being produced would be acidic in nature. All right, which leads us into our last kind of category, which would be our amphoteric oxides. So aluminum oxide, a little bit easier to measure its reactivity in water. It doesn't affect the pH when added to water because it's basically an insoluble salt, right? You think about its KSP value, it would be relatively low. It would take a very small amount of aluminum oxide is going to dissolve in water, so we'd say it's pretty much insoluble. Now, it does show amphoteric properties because it can act like an acid or a base depending on other factors within your solution that you're dealing with, right? And so, for example, when aluminum oxide reacts with sulfuric acid, it behaves as a base. So the aluminum oxide reacts with it, undergo an acid-base reaction, helps neutralize the sulfuric acid, you get water, and you get aluminum sulfate that's being produced, right? Now, on the flip side, if it's placed with a base, for example, then it's going to behave as an acid instead of neutralizing or taking on taking the H away from the acid to make water. In this case, it's going to be donating its H to interact with the base to help neutralize it. All right, and so that's all we've got for that particular section. Just wanted you guys to be aware of that, of kind of the differences that we have here with the oxides of period 3. And it is important for you guys to kind of know those reactions that I introduced to you in this video. It'd be important to know those because that's something that want you to be familiar with. So hope this was insightful. Hopefully it was helpful. And I look forward to seeing you guys again in class. Take care. Bye-bye.